Good day, students. So today we're going to take a look at section 9.6 today. All right, so I ask everybody to randomly sample 36 UA students, and you ask them what their age is, and then you go ahead and calculate the sample mean. So you take the average of the 36 UA students, all right? So the first person reports back to me, and the first person got an average or a sample mean of 19.7. So notice here I put an X bar, right? That's the sample mean, okay? And turned out to be 19.7. The second person, when they calculated their sample mean, their sample average, if you will, came out to 20.1. Now, why was it different from the first one? Well, because the second person brought in probably 36 different people than the first person. You know, with a campus of 20,000 people, if I told you to just randomly pick 36 people, well, probably the first and the second student is going to pick 36 different people, okay? Well, the average turned out to be 20.1. What about the third person? They came out with an average of 19.9. Well, just imagine that we didn't do this just for the 36 UA students. We did this for a whole bunch of times and for every possible sample. All right, so for every possible sample, so the very last sample that we could possibly get, we got an average of 20.2. Well, is everybody okay with this? Meaning that X bar varies from sample to sample. It just depends on the 36 UA students that you brought into your sample. And hopefully everybody says, yeah, that seems reasonable. Okay, that's what we're studying today, how X bar varies. So let's summarize a couple of things. Okay, first thing is not X bar, but X. X here. X is a random variable that can vary from person to person or thing to thing, like age, time, weight, okay, so on and so forth. X can also vary from sample to sample, just like the binomial random variable, number of successes out of a certain amount of trials, and think of number of trials as a sample size. All right, and so X can also vary from sample to sample. But generally speaking, okay, when we talk about this stuff and we do these problems in inferential statistics, normally what's going to happen is that X is going to be there's going to be an underlying variable there, and X is going to vary from person to person or thing to thing. Okay, P hat from the last video lecture is a sample proportion. The reason why we looked at P hat was because the variable that we started with is categorical. Remember, like corrective lenses, does a person wear corrective lenses or not? So for yourself, you would either answer yes or no, right? It's non-numerical, it's categorical. Okay. Once the underlying variable is categorical, you know, the data that we collected is categorical, probably we're going to look at proportions. Thus, p hat for a sample proportion. X bar, what we're studying today, is a sample mean. And the reason why we've changed over is because now the variable is quantitative, okay, like age, all right? Now notice p hat and x bar, they're both statistics. Why? Because they're both coming from a sample. They're sample measurements. They're statistics. So what we're finding out is that statistics are random variables, okay? And all statistics vary from sample to sample. That's what we have to study here, okay? This is important to understand why inferential statistics works. All right, let's move on. So before we learned how X, this is X, okay, let's say X is discrete, we study it by studying its probability distribution. So remember, we could put it into a table and we said, here's the values that big X can take on, and it would be 0, 1, 2, 3, right? Okay, well now we have to study how X bar varies, okay? How X bar varies, and that's sampling distributions, okay? So today we are studying the sampling distribution of X bar. So imagine the following. Again, we go back to our problem where that we sampled 36 UA students, right? And ask what their age is. And then imagine that for every possible sample that we calculate, that we could possibly get, we go ahead and calculate an X bar for each possible sample, okay? And then for the uh, uh, we're going to put all the X bars that has exactly the same sample size into one place. We're going to put them all into a histogram. And what's going to happen is that histogram is going to exhibit certain characteristics. Those characteristics we have to study today. Okay. Now, before we get to those characteristics, the symbol that we're going to use for the sampling distribution of X bar is an X bar with parentheses around it. Once you see that, we're talking about the sampling distribution of X bar. And remember, we always want to investigate three things about a sampling distribution. Its mean, standard deviation, and its probability distribution, right? What kind of shape is it taking on? I kind of interchangeably use shape and probability distribution. A lot of textbooks do that, okay? All right, for the sampling distribution of X bar, what you got to imagine here is that we took all those X bars from that histogram, okay, all those values, all those possible values, and averaged all of them, okay? That's what we're talking about when we talk about the mean of the sampling distribution of X bar. What's the expected value? And then what would be the standard deviation of the sampling distribution of X bar? If we took all the values of all those X bars and then took the standard deviation of all of them, okay? Well, there's a whole bunch of them, and so we really don't want to actually have to do the math, okay? Because there's too many of them, okay? But there's shortcuts to this, okay? There's shortcuts to this, just like we saw with the sampling distribution of p hat, all right? So what we found out is that if you averaged all possible X bars in the sampling distribution, okay, if you could theoretically do that, the average would always come out to the exact value of whatever mu was. It's as simple as that. Whatever the population mean is, whatever that value is, that's going to be the mean of the sampling distribution of X bar. 2, be careful with this one. What we find out here is that the standard deviation of all those X bars is equal to sigma divided by the square root of n. So what's sigma? Sigma is the population standard deviation. That would be the standard deviation of all the x's. All right? And if we divide by the square root of n, believe it or not, we would get how all the x bars are varying now, okay? We would get the standard deviation, the sampling distribution of x bar. Be careful with that one, but we're going to go over some examples here to show you and remind you of that. Now, this indicates two things. The first one I talked about in the with regards to the standard deviation of p hat. Okay, what we found out is that as n increases, the standard deviation of the sampling distribution of x bar decreases. So as n goes up, the standard deviation of all these x bars goes down. So for example, let's say sigma is equal to 24. So that's the standard deviation of all the x's. N is equal to 36. If we do the math there, what we find out is that the standard deviation of x bar, of all those x bars, is only equal to 4. Notice that 4, okay, that the standard deviation, see if I can get my pen out. No, it's not allowing me to get my pen out. Hold on. There we go. Notice here that the standard deviation of the sampling distribution of x bar is 4, and sigma is 24. So the standard deviation of x bar is always going to be lower than the standard deviation of x. Okay. So let's go ahead and increase n from say 36 up to 64. What's the standard deviation now? So since n is going up, the standard deviation of all these x bars should be going down, right? If you do the math, notice it. So as n increased from 36 up to 64, what happened to the standard deviation of the sampling distribution of x bar? It decreased. Okay. Now, what's the second thing is this is indicating to us? Well, what this is also indicating is that as n changes, we get a different sampling distribution of x bar. Okay, so we get a different sampling distribution of X bar every time, and moves around. Okay, so like here, when it moved from 36 to 64, the standard deviation went down and it got a little skinnier, meaning the graph of the sampling distribution of X bar got a little skinnier. So you get a different sampling distribution at every different end. All right, what about the third part? Which probability distribution does it take on? Meaning its shape. Okay, now there's two rules here. Unlike the sampling distribution of p hat, where there's just basically one rule, okay, there's two rules here, okay? So here's the first part. First part says, regardless of how large the sample size is, the sampling distribution of X bar will be approximately normal if X is normal. So if X is normal, so if X is taking on a nice bell-shaped curve and it's looking awfully normal to us, okay, and we go ahead and sample from there, and we create the sampling distribution of X bar, okay, put all the X bars together into one spot, that shape of the sampling distribution of X bar will be what I'm calling approximately normal. I'm putting that in quotes. You'll see why when we get to inferential statistics, why I'm calling it approximately normal, okay? It's almost normal. Then two, if X, the original population, is not normal, well, we have a whole bunch of variables that aren't normal, okay? Like age of college students. Age of college students is absolutely positively skewed to the right, okay? We got a whole bunch of students that are 18, 19, 20, 21 years old, and then we got some students who are older, but not that many, okay? And we got variables that are skewed left, such as GPA, test scores, okay? So what about those variables? Can we still say something about the sampling distribution of X bar for those variables? Well, okay, what we find out is that for a population that starts off non-normal, it's not bell-shaped, okay, the sampling distribution of X bar will be approximately normal if the sample size is greater than or equal to 30, okay? And remember what we called this? We called this the central limit theorem, okay? This is just the rules for the central limit theorem with regards to the sampling distribution of X bar. So we got to keep the rules for the sampling, the rules for the CLT straight with regards to X bar and P hat, because there's different criteria. You need to memorize those. Okay. Here, as long as n is greater than or equal to 30, the standard, the central limit theorem will apply, and the sampling distribution of X bar again will be approximately normal. So let's do a problem here to clarify what we're talking about. All right, so there's a concern of how cars are driving the Ohio Turnpike. I say cars because we're not going to be looking at trucks, just cars. Assume that the speed of all car drivers on the Ohio Turnpike are normal, or if you will, you might see the problem say normally distributed. Okay, the mean of 80 and the standard deviation of 4 miles per hour. We take random samples of 100 car drivers repeatedly. Okay, so we do this over and over and over again. We calculate an X bar for each one of those samples, and we put all those X bars into a histogram, and we create the sampling distribution of X bar. Okay. All right, so let's write down what we know. We know that X, car driver speed, right? Car driver speed, and those speeds are varying from what? Person to person. Okay, so X here is varying from person to person. Mu is equal to 80. Why did I say mu? Because I said all of the drivers have a mean of 80. So that's why I put mu there, the population mean. Population standard deviation is equal to 4. Okay, and all of our samples will have a sample size of 100. All right, so what is the probability distribution, the sampling distribution of X bar? So what's the probability distribution? Okay, so since X is normal, remember we said X is normal here, right? So since X is normal, the sampling distribution of X bar will be approximately normal, okay? Almost normal. All right, what about the mean of the sampling distribution of x bar? All right, we said in value, that should be equal to what? Mu. So it should be equal to simply 80. It's the value of mu. Then what is the standard deviation of the sampling distribution of x bar? Be careful. This is the standard deviation of the sampling distribution of x bar, not of x, not of the car driver's speed. Okay? We're talking about the standard deviation of all these x bars. Remember, what do we have to do? We have to take sigma and divide it by the square root of n here. Sigma is equal to 4. N is equal to 100. The square root of 100 is 10, so 4 divided by 10 is 0.4. Okay? So those questions by themselves are pretty simple. But what really makes this happen is a couple of graphs. So let me show you the first graph that I want to make here. Okay? This is the graph of the sampling distribution of x bar. So these are all the possible x bars that we could have possibly have gotten where n was equal to 100. Notice what I put here in the middle. I put 80, the mean of the sampling distribution of x bar. Could also call that the expected value. The standard deviation was equal to 0.4, right? So I went out one standard deviation here, another one here, one here, one here, one there, right? If I drew a line right here and right here, so here's my question to you. What percentage of all the samples will produce an X bar between 79.6 and 80.4? And hopefully you say, oh, based upon the empirical rule, that's 68%. Okay, so it doesn't matter that we have billions or maybe even trillions of X bars that we could possibly get. Okay, it doesn't matter. We know 68% of them are going to be contained between what? 79.6 and 80.4. What about from here to here? What percentage of all samples will produce a sample mean between 79.2 and 80.8? Hopefully you said, oh, 95% about empirical rule stuff, right? And then if we want out one more standard deviation, we would be at 78.8 and 81.2, right? And about 99.7% of all possible samples of size 100 would produce an X bar between those two values, okay? Could we get an X bar outside of there? Yeah, but it's very unlikely. Okay, it's very unlikely. So this is powerful stuff. Even though we have maybe billions or trillions of X bars, we know that most of them are going to be contained in a very small area. Now, I got what I want to do is I want to compare this graph to the original graph of X. This next graph, next two graphs, I should say, are very important, okay, to understand. Okay, so the graph that we just made is actually this one down here. So this graph that we just made here is actually this bottom graph here, all right? This graph up here, the top one, this is of X. This is how X varies. This is how those speeds are varying, okay? And so we have a mean of 80 and then standard deviation of 4, right? So maybe here's the first standard deviation, here would be the second standard deviation, here would be the third standard deviation. Notice we have hardly anything out there past that. We go out one standard deviation this way, one standard deviation that way, and over here at about what, 68, we have hardly any more data, okay? So this is how X varies, okay? This is the histogram for X. Here, this bottom one is this graph right here. Notice how much skinnier it is, okay? Notice X, even though X could be 72, is it likely to get an X bar of 72? Nope. Why? Because they're very much contained right in here, okay? Remember, they're contained pretty much between 78.8 and 81.2, and for the most part, most of them are actually probably, you could say, between 79.2 and 80.8, okay? So why is this so much skinnier than the top one? Remember, sigma up here was equal to what? 4. What was sigma here? Well, I shouldn't say what was sigma down here, but what was the standard deviation down here? Well, this was only what? 0.4. Okay, because remember, you got to take and divide that 4 that we have up here divided by the square root of n. Okay, so notice how x bar is much, much skinnier. The sampling distribution of x bar is much, much skinnier than x. So even though x can vary, anywhere from say 68 to 92, okay, maybe it could get a little bit further out than that, but for the most part, it's going to be contained within those two values. X bar, X bar is going to be contained between what, 78.8 and 81.2, and for the most part, it's even a little bit skinnier than that because 95% of them are going to be contained between what, 79.2 and 80.8. Okay, that's important stuff there. Here's a second example. Weight for all male U.S. adults are skewed right, with a mean of 186 pounds and standard deviation of 40. We take random samples of 256 probably male U.S. adults repeatedly. Probably have an extra S there. Okay, so what do we got here? We got X is equal to weight for a U.S. adult male. That's the underlying variable. It is what? Quantitative, thus we're looking at means. Okay, that's X. Mu, the mean of all those X's, mean of all those weights is 186. Standard deviation is 40. That's why we use sigma. And we took a sample size of 256 repeatedly over and over and over again. Okay. What is the probability distribution of all these X bars? So we put all the X bars together into one graph. What is the probability distribution going to look like? Well, let's see. The original distribution X is what? Skewed right. It's skewed to the right. Okay? It's not bell-shaped. But can we say something about the sampling distribution of X bar? Well, yes, we can. Why? Because of the central limit theorem. As long as it's greater than or equal to 30 in this situation, okay, it's 256. The sampling distribution of X bar will be, again, approximately normal. What about the mean of the sampling distribution of X bar? Well, it should be in value going to be equal to mu. So that's just simply 186. No big deal there. So that's the expected value of the sampling distribution of X bar. What about the standard deviation of all these X bars? Okay, be careful. Remember, you got to divide through by what? The square root of n. Okay, so we got 40 divided by the square root of 256. And we get what? 2.5 when we do that calculation. Okay, so let's make a graph. Again, this is the sampling distribution of X bar. Okay, and notice mean is at 186, standard deviation is 2.5, okay? So 2.5 for the standard deviation. So what does that mean? We drew a line here, we drew a line here. We know that 68% of all the samples will produce something between 183.5 and 188.5 for a sample mean. And then you can keep on going for 95 and 99.7, okay? So notice it's pretty much all of them are going to be contained between what, 178.5 and 193.5. Okay. All right. So now we take this graph and we put it on this graph here. And notice the graph that we just made is actually this bottom one. Okay. This is the sampling distribution of X bar. That's how all the X bars vary. This guy up here is X. Notice it's skewed to the right. Okay, skewed to the right. Its mean is at 186. okay? So this is how x varies, okay? And so remember, how is x going to vary? How are we going to measure it with sigma, okay? Why is this so much smaller? Because the standard deviation of all these x bars is sigma divided by the square root of n. And so the bottom one, the, the, uh, um, the standard deviation of the sampling distribution of x bar is always going to be smaller than the standard deviation of x, okay? Because we're dividing through by what? Square root of n. And that, remember that this had a sample size of what, 256, okay? And so we divided through by 16, okay? And notice that these x bars are looking approximately normal. You'll see what distribution it actually takes on when we get to inferential statistics, but for right now, we'll just say approximately normal, okay? So this is showing you the central limit theorem. So x was skewed to the right. That's okay. When we put all the x bars together, believe it or not, it's not going to be skewed to the right as long as n is greater than or equal to 30. And that's what happened here. Okay? All right. Thank you for your time today.